Hello, everyone. I'm Jinyin Hu, a first-year PhD student from Australian National University. My two supervisors are Dr. Pham and Professor Kalchich. Now I'll introduce our studies on probing earthquake sources by a new method. According to Geoscience Australia, there's on average 80 earthquakes of magnitude 3 or more in Australia each year. Australia's largest recorded earthquake was in 1988 at Tennant Creek in the Northern Territory with an estimated magnitude of 6.6, but it was not in a populated area. A magnitude of 6.5 earthquake at McCurran in 1968 caused extensive damage to buildings and was felt over most of the southern Western Australia. Earthquakes of magnitude 4 or more are relatively common in Western Australia, with one occurring about every 5 years in the McCurran region. And based on the data from Geoscience Australia, since October 2020, 483 earthquakes happened in Australia. And among them, the biggest one is the Melbourne earthquake happened on 2020 September this year. In Melbourne, its magnitude is 5.9, caused widespread damage in Melbourne and sent shock waves to several states from the shock map we can see. It happened underground and caused so many damage. Now, so how do we learn about it? Firstly, an earthquake is the shaking of the Earth's surface. There are various earthquake sources, such as the moving of the tectonic faultings, volcanic eruptions, landslides, underground explosions, and glacier moving, and so on. These sources can produce seismic waves that propagate along the solid Earth, and they are recorded by our seismometers at distances. So the recorded signals at different stations are key to infer the earthquake sources. So how to differentiate these different sources and know their character based on the recorded seismic signal? This answer is to use our seismic source invariant. A seismic source invariant is a procedure to infer about the physics of the source by fitting predictions obtained by forward modeling and the seismic observations. To do that, firstly, we need to generalizedly represent these different sources mathematically and try our best to include all possible source types into one method. Secondly, analyze the solution uncertainty is a leading edge topic today, and the uncertainty can be caused by the Earth structure error and the data noise. So these concerns are what we are trying to solve in this study. Here, we provide a solution for that. We use a more generalized source representation in our method to explore a wide range of the earthquake source. We did the source invariant in the Bayesian framework because it has a great advantage to do uncertainty estimate. In Bayesian theorem, the probability of each solution M is proportional to likelihood function and our prior information about the source. The likelihood function measures the fitting level between observed data and predict data. Based on it, our method decides if accept each updated source model. To consider a complete uncertainty estimate, we combine data noise and the structural error in our covariance matrix CD here. So how to estimate the uncertainty for data noise and the structural error? To do that, firstly, to estimate the uncertainty caused by structural uncertainty, we randomly perturb the reference Earth model as shown by black line in panel A. This model is an estimate of the true Earth model because the true Earth model is unknown. After perturb the Earth model, say 300 times with a given percentage, uncertainty percentage, say 5%, I get 300 structural models of the gray color shown here. Then with these 300 models, we can calculate 300 waveforms for each station. We computed the covariance matrix of structural uncertainty, like shown in figure C. Also in figure B, you can see when moving to high frequency bands such as 10-second to 50-second period used here, there are obvious time shift between the waveforms obtained from the reference model and our true Earth model. That is why structural uncertainty is necessary to consider in a higher frequency band. It is significant in source invariant. In this work, we propose a method to partially solve that problem. For data noise, we consider the uncorrelated noise with a diagonal matrix using the percentage of the RMS of the data. So to validate our method, we did a lot of synthetic experiments in different geological settings. For example, here is a test case located in North Korea. This is the map of a region showing the earthquake location like Black Star and the 10 seismic stations used to generate waveforms and use them as they recorded signals. To model the real scenario, we added the real noise of each station into the synthetic data. As shown here, we did many times tests to inverting for different types of sources. Each time, the method can recover it very well. We can see here the difference between the inverted source and the input source are very small. This means they are almost the same. So we can see this new source invariant method is reliable. It will provide a powerful tool to monitor underground nuclear test. We are also looking for other events such as the Bajibanga earthquake. This is an example. The earthquake happened in 1996. Its magnitude is 5.6. It was recorded well by the regional scale Iceland hotspot project seismic experiment. Previous studies showed that there is no net volume changes during this eruption. So with our new source invariant method and this well-recorded data, we will hopefully reveal this puzzle and help us to understand more about the volcanic eruptions. We also will study the source of a Melbourne earthquake. For this earthquake, there are good station network covering the continent continuously and recorded rich data for these earthquakes. This earthquake is well covered automatically by the seismic stations. So this will greatly help us studying it, and all other earthquakes happened in Australia. So finally, we want to introduce our new method. This method combined two types of source representation. That is moment tensor and single force in one method, and they also consider both data noise and the structural error. We are hopeful this will provide further insight into the physics of seismic source in various settings, including underwater landslide and the glacier interaction in the Australian surroundings when the data is available. So thank you for your attention.